Good evening, guys.
Good evening.
So today's topic, good evening. So today our topic of discussion is going to be the last part of this chapter, which is optical instruments. So if you see the name of this chapter, it is ray optics and optical instruments, right?
Yes, sir.
So the last part that we are going to concentrate upon is optical instruments. So first, let's try to understand what an optical instrument is. Basically, an optical instrument is a device, right? It is an optical device which is constructed by suitable combinations of mirrors, prisms, and lenses so that it assists the eye in viewing an object. This is the most important point. Means, majorly the optical instruments are used to enhance something and see. Right? To enhance something and see, we use the combinations of mirrors, prisms, or lenses, or any such combination we take into consideration. Right. So the most commonly known optical instruments that we see in our day-to-day life, projection instruments, basically like projectors, which are there in your school also. Like your teacher would have connected it to a laptop and projected the data onto the screen. So projection devices. Similarly, we can think of microscopes, right? When you think of microscopes, we have, so why do we use a microscope? So microscopes are basically devices which are used to magnify smaller sized objects. So in microscopes, you have both simple microscope and a compound microscope, right? Similarly, the last device that you have is a telescope. So telescope is basically used for looking at the astronomical and distant objects. So you look at them in magnified form, which otherwise cannot be seen with the naked eye. So generally we use an astronomical telescope, a Galilean telescope, a terrestrial telescope, a reflecting telescope, etc. All these things are do fall under the category of telescope, which is mainly used for viewing the objects at a greater distance, right? So before we start studying about these optical instruments, there are certain terms that you need to understand with respect to these optical instruments, of which one of them is called as the visual angle. So what exactly is this visual angle? It is something like this. So if you look at the size of an object as perceived by the eye, so you have an object in front of you, right? And that eye is going to see that particular object. It depends upon the size of the image which is formed at the retina, because retina is the place where this image is captured. So the size of the object perceived by the eye depends upon the size of the image which is formed at the retina, right? So the size of the image formed at the retina is generally what is roughly proportional to the angle subtended by the object of the eye. We need to understand this concept. Let me tell you what it means. So if you take this eye, right? So in this eye, you place an object in front of it. What are you doing? You're placing an object in front of it. So from here, you take a line. You take a line along the horizontal. So why I took it is because I took it from the two endpoints of that object. Then I get the size of the image. So the size of the image is, I'll call this image as I1. Similarly, the same object is moved to a longer distance. At this point, what is happening is, if you take the ray from the top end and the bottom end, you are able to observe that there is another image that is formed. Now, logically tell me which image is bigger compared on a comparative basis. Now, which image is bigger on a comparative basis? It is I1, which is greater than I2. So when I say I1 is greater than I2, I am also able to see, one minute. When I say I1 is greater than I2, I am able to see the fact that theta 1, right? Theta 1 is of a greater value compared to theta 2. You're able to see it, right? So this angle that is formed at the eye, where you take the rays from the end points of the particular object, is what is called as visual angle. So the two visual angles that you're able to see are theta 1 and theta 2. And when the object is, so it is mentioned here, see, when the object lies close to the eye, its visual angle is large, and hence the image I1 is formed at the retina is large. When the object is taken far away from the eye, its visual angle becomes small, and hence the image I2 is formed at the retina, and it is observed to be small also. Right? Now see, if theta 1 is the visual angle subtended at the eye for near position of the object, and theta 2 is the visual angle subtended at the eye for the far position of the object, we are clearly able to discriminate the fact that theta 1 is greater than theta 2. Similarly, I1 is greater than I2. Right? Okay. So optical instruments are basically used for what? They are used for increasing the visual angle artificially. Right? Artificially means they act as a source to increase the size of the visual angle by following certain mechanisms. Okay. So as what you can have is you can increase the size of the image formed at the retina. So more is the size of the image that is formed at the retina, more is the detail that you're going to have. Right. So having all these things in mind, let me tell you the first point that we are going to concentrate upon is the magnifying power or angular magnification. So whatever optical instrument you're going to study about, the major point that you'll be concentrating upon is the magnifying power or angular magnification. So let's try to understand what this magnifying power is. So magnifying power or angular magnification, they both mean the same. So this term magnification is not new to you. Right? What does magnification mean? So magnification basically is the ratio of the size of the image to the size of the object. Ratio of size of image to, sorry, size of image to size of the object. Am I right? But what is this magnification we are trying to talk about? This is what we call it as linear magnification. Right? But what are we trying to talk in this context? Magnifying power also has another name called as angular magnification. So what does angular magnification mean? So for microscope, so listen to this carefully. Magnifying power or angular magnification is generally represented by the symbol capital M, which is the factor by which an angle formed on the retina can be enlarged by using a microscope or a telescope. So when you take a microscope, the magnifying power is taken something like this. It is the ratio of the visual angle subtended by the final image at the eye to the visual angle subtended by the object at the eye when kept at a distance called as the least distance of distinct vision. So it is very simple. Listen to this carefully. I want everybody to write this. So write capital M with a subscript microscope. So the magnifying power of a microscope is defined like this. It is defined as the visual angle subtended by the final image at the eye divided by the visual angle subtended by the object at the eye when kept at the least distance of distinct vision. Okay. Similarly, if you take a telescope, for telescope, what you happen is the magnifying power is defined as the ratio of the visual angle subtended by the final image at the eye to the visual angle subtended by the object at the eye when seen from the naked eye. Okay, if you observe, the numerator is the same in both the cases, but if you look at the denominator, in the case of microscope, you use the word capital T, which is called as the least distance of distinct vision, whereas in the case of telescope, you use the word seen with naked eye. Naked eye means without the help of any optical instrument. right? Now, I have to explain what this least distance of distinction means. Least distance of distinction. It is also called as the near point. Okay, least distance of distinction is also called as the near point. So what it actually means is, it is the minimum distance at which an object is to be placed so that we are able to see the object clearly without a strain. What I'm trying to say here is, suppose you have pen in your hand, right? This is your eye. If suppose you keep the pen here, if you keep it this close, what will happen? So if you keep the pen this close, then you can observe that. What is it you can observe? You can observe that there is going to be a strain in your eye, right? So for that strain to be reduced, what will you do? You will slowly move this pen to a greater distance. Let's say you're moving it to this distance, at which you're able to see the top to bottom of the pen without any strain in your eye. Then this distance is what is called as the least distance of distinction or near point. Generally, for a healthy eye, it is taken to be 25 centimeter. Means for a normal eye without the help of any spectacles, right, which doesn't have the eye which doesn't have any defect, what you generally do is you try to keep the object at a distance of 25 centimeter from the eye so that you are able to see the image clearly, that you are able to see the object. So that is what we call it as the least distance of distinct vision. Okay. So having said this, now we are going to see the concept of a simple microscope, which is also called as a magnifying glass. So simple microscope is nothing but a simple convex lens. So this is the point you need to make a note of. So generally, if you take a convex lens of short focal length, what are you going to do? You're going to take a convex lens of short focal length. Then it can be used to see magnified image of small object and is called as magnifying glass or a simple microscope. Right. So what I'm trying to say here is, basically when you take lens, there are two types of spherical lens that we can speak about. One is a concave and the other is a convex. So basically, what is a concave lens? So concave lens is the one which can always form a virtual image, right? If you take convex lens, so convex lens has the capacity to form a real image and a virtual image. But if you do a comparative study, concave lens will always form a virtual image. I repeat it, concave lens will always form a virtual image, which is always diminished. Whereas when you talk about a convex lens can form a virtual image which is magnified. This is the only advantage. So this is the only place or the only device which can produce a virtual and a magnified image. That is why if you see a convex lens is what is used as a simple microscope. Okay. So generally when you place an object in front of, I repeat it, generally when you place an object in front of any optical instrument, you need to ensure that there is a virtual image that is formed by it. What is that you need to ensure? You need to ensure that there is a virtual image formed by it. Right. So when a small object is placed between the optical center and the focus of convex lens, its virtual, erect, and magnified image is formed on the same side as that of the lens. So virtual image with respect to a lens means object and lens, object and image, they both are on the same state. Okay. So the lens is supposed to be held close to the eye and the distance of the object is adjusted till the image is formed at the least distance of distinct vision from the eye. So what you're supposed to do is listen. Suppose I give you an object. I told you about the pen, right? Suppose I give you the pen. Okay. So first you need to observe this pen with the naked eye. And let's say the angle that is getting subtended at your eye is alpha. The height of the object, I'll call it as h0. Okay. Then what is the minimum distance at which you can have this kind of a clarity? That is the least distance of distinct vision. Okay. So having this in mind, if I start introducing a convex lens between the object and eye, then what will happen is the object will appear in a magnified form. There is a magnified virtual image that we form due to the convex lens, provided you place that object between the focus and the optical center. Okay. So when the image is formed at the least distance of distinct vision, or we call it as the near point adjustment, or generally it is also called as strained viewing, because you need to strain your eyes a bit to see the position of that image. That is literally you have to close one of the eyes and then actually look at it. Okay. Then what is going to happen is, see. So there will be two cases, guys. Case one is you need to ensure that the adjustment is done in such a way that the final image is formed at the least distance of distinct vision. And the second scenario is you need to do the adjustment in such a way that the image is formed at infinity, such that the image is formed at infinity. Okay, listen. So if I place the optical instrument here, I place the convex lens here. Okay. Now, if I say that this is the object, okay, let this be A and B. And if I take a ray parallel to the principal axis, after refraction will pass through the focus on the other side. If I take a ray through the optical center, then it is going to travel like this, right? So if I say this is I, then what will happen is these two rays will get diverged in such a way then I can say that these two rays are going to get diverged in such a way that there is a virtual image, which is going to get formed here. Okay. Which I call as the height of the image. Okay, what did I say now? You need to keep the object between the focus and the optical center in such a way. The first case, the adjustment is to be done so that the image is formed at the least distance of distinct vision. Okay. Now see, if I take the projection of this onto this part, from here, I can draw a ray like this. Now, this angle that has got subtended is beta, and this angle is what is called as alpha. Okay. And this distance is u, and this distance is f. Now listen to this. The magnifying power of microscope. So the magnifying power of microscope when the image is formed at the least distance of distinct vision is given as the ratio of angle subtended by the final image to the angle subtended by the object at the eye. And remember, this height is h0. So beta divided by alpha is nothing but tan beta divided by tan alpha. So what is tan beta? Tan beta, if you see, it is the height of the image divided by the least distance of distinction divided by what is tan alpha? Tan alpha is going to be h naught divided by d. H naught, d and d will get cancelled. It will be hi divided by h naught. Means the magnifying power of a microscope is exactly equal to the linear magnification that has occurred. Is equal to the linear magnification that has occurred. So try to understand that magnifying power is angular magnification, but this theory is telling that the angular magnification is exactly equal to the linear magnification in the case of a simple microscope. If that is going to be the scenario, hi divided by h naught, then we know that linear magnification with respect to a convex lens is also given as b divided by u. Okay. Now I'll call this as equation number 2. Now applying lens formula. Applying lens formula, 1 by v minus 1 by u is equal to 1 by f. So 1 by v minus 1 by u is equal to 1 by f. 1 by v is minus d minus 1 by u is minus u is equal to 1 by f, which implies minus 1 by d plus 1 by u is equal to 1 by f. Now multiply with d on both sides. So you will get minus 1 plus d by u is equal to d divided by f. Remember, v by u is the linear magnification. V is nothing but d and u is u only. So d divided by u is going to be the angular magnification. So minus 1 plus md is equal to d divided by f, which implies md is equal to 1 plus d divided by f. Okay. And copy this. Right?
Yes, sir.
Okay. Now the next concept is the same simple microscope, when the image is formed at infinity. So when the image is formed at infinity, it is also called as far point adjustment or relaxed viewing. Okay. Now listen. If the image has to be formed at infinity, okay? If the image has to be formed at infinity, where is the object supposed to be placed? Is the question. Right. So the object is supposed to be placed at the focus. The logic is very simple. When you place the object at infinity, the image is formed at focus. So when you place the object at focus, the image is formed at infinity, as simple as that. Right. So when the object is placed at focus, what will happen is the rays will get refracted in such a way that the final image itself is formed at infinity. So from here, if I take a line parallel to the object and take the angle calculation, then this is going to be alpha and this is going to be beta. So this is a very simple derivation. So this height of the object, this height of the object. Here u is equal to f, and here this least distance of distinction is going to be d. So what is tan alpha? H naught divided by d, and tan beta is equal to h naught divided by f. And we know that the magnifying power of the lens when the image is formed at infinity is equal to tan beta divided by tan alpha. Tan beta is h naught by f divided by tan alpha is h naught by d. H naught and h naught will get cancelled. D divided by s is going to give you the magnifying power when the image is formed at infinity. So in both the cases, you're going to have magnification. But if you observe here, when the image is formed at infinity, the magnifying power is 1 unit less than what has occurred in the previous case. But the advantage here is the view that you're going to have is going to be more comfortable. Okay. So this is the derivation, simplest derivation that is possible when the image is formed at infinity. Right? I hope it is clear, right?
Yes, sir.
Right. So I'll be sharing this document after this class. You can read this everything on your own. Now we will do a problem which is based on simple microscope. So listen to this. There is a man with normal near point. Normal near point means it is basically 25 centimeter. Means he doesn't have any defect in his eyes. He reads a book with a small print. The book is having a small print and he is using a magnifying glass, which is a thin convex lens, and that magnifying glass has a focal length of 5 centimeter. Now the question is, we need to find the closest and the farthest distance at which he can read the book when viewing through the magnifying glass. Okay, we need to find the closest and the farthest distance at which he can read the book when viewing through the magnifying glass. Second is maximum and minimum magnifying power possible using the above simple microscope. So these are the two questions that we need to solve. If you observe, two important points that are given in the question are D is equal to 25 centimeter and F is equal to 5 centimeter, as simple as that. Right. So closest and the farthest point at which he can read the book when viewing through the magnifying glass. So when he's viewing through the magnifying glass, what is the closest distance at which the image can get formed? The closest
25
distance at which
centimeter.
that's it. So 25 centimeter. So the closest V minimum is going to be 25 centimeter. But remember, object and image, since they both are on the same side, you have to put a minus sign. Sharia. So it is minus 25 centimeter. Similarly, what is the maximum distance at which the adjustment can be done so that the image is formed? That is when you place the object exactly at the focus. It is infinity with a minus sign because object and image are on the same side. So V max is minus infinity. Right. Now the next question is, we need to find the maximum and the minimum magnifying power possible by using a simple microscope. So we know that the magnifying power of a microscope has two cases, MD and M infinity. MD is 1 plus D by F, M infinity is D by F. Accepted?
Yes, sir.
So MD is equal to 1 plus D by F implies it is 1 plus, what is the value of D?
Minus 25 centimeter.
This is where you need to be careful, okay? So
Oh,
I
yes,
told
sir.
you need to apply, and it is not minus 25 now. That
Plus
is what I was about
25.
to say.
Yes,
Is
sir.
it plus 25? Why?
Because we use sign
So that's what,
convention.
if you use sign convention, the D is on the left hand side, no? U and D are on the same side, no? Then it should have been minus only according to your logic.
Yes, sir.
Yes, no, but we'll use only plus. I'll tell you the reason. Listen to us carefully. So I would have told you, right, in this chapter, when you're using sign convention, you need to use it during the process of derivation and you need to use it during the process of solving problems also, right? I mentioned this. But if you take the scenario, if you look at the possibilities where I told you can do this is for the case of mirrors, for the case of lens, right? Why did we do that? I told you the logic there also. Why did we do that? Can you tell me? Because when we derived something called as a mirror formula, for mirror formula to be derived, we need to take how many scenarios into consideration? How many mirror diagrams are possible? Mirror ray diagrams are possible. There are 8. So including plane mirror, it is 9. Similarly, when you
Yes,
talk
sir.
about diagram, it is 8 ray diagrams. But if you see the derivation, we would have used any one of the conditions. Correct? So using any one of the conditions, we have applied sign convention. While solving the problem, we don't know for which condition that formula was derived. So we are trying to nullify it. But in this case, what has happened is this 1 plus D by F is there, right? You got this 1 plus D by F by applying sign convention only. Paranga. You got it by sign convention only. Observe, I applied minus D here, and the focal length of the convex lens is positive, right? But
Yes, sir.
this situation is there, right? This situation of where you place the object between the focus and the optical center so that the image is formed at the least distance of distinction. It is only one scenario. So when I say it is a one scenario basis, it is a sure shot scenario. When it is going to be a sure shot scenario, since you have applied the sign convention in the derivation process, you need not apply the sign convention again, because for something which you are sure of, you're not going to apply sign convention. So 1 plus D divided by F implies 1 plus, how much is the value of D? It is
25.
plus 25 divided by 5. I hope I convince like
Yes, sir.
your explanation, right? So it is 5, it is going to be 6. So magnification is 6. And what about this case? And what about the other magnification? D divided by F. It is 25 divided by 5. It is going to be plus 5. Accepted?
Yes, sir.
Right? It is 25 divided by 5 is going to be plus 5. So what is the maximum magnification possible? Maximum magnification possible is 6 and minimum magnification possible is 5. So when will the maximum magnification scenario occur? When the final image is formed at the least distance of distinction. And when is the minimum magnification scenario going to occur?
Image at infinity.
When the image is formed at infinity. Okay, so what you're supposed to do is when you're studying about the optical instrument, you need to be clear about the two scenarios. So you need to have a good grip of the ray diagram, and you need to have a good grip of the derivation as well. Right. So I hope I have answered that. Right. So this is all about simple microscope. Right. So I'm hoping that everything is clear. So what are all the things that we concentrated upon? First, we try to understand what is visual angle. Once you're clear with visual angle, you need to ensure what is magnifying power or angular magnification. Once that part is over, you need to understand the ray diagram with respect to a simple microscope. Right. So in that scenario, you will be considerate about two cases: when the image is formed at the least distance of distinction and when the image is formed at infinity. Then using those two formulae, you need to know how to apply them. So the thumb rule that you need to have in your mind is, while applying the formula for simple microscope, while applying the formula of magnification for simple microscope, you need not apply sign convention in the problems. Okay, these are all the rules. So having all these points in mind, if I have to give you an outline of what is a compound microscope, here, this is also a microscope only, but the prefix that is added here is a compound. So the word compound has come because here we will use a combination of two lenses, right? So if you see, compound microscope is mainly used in observing microorganisms. You'll use it in your biology lab, right? Those who are biology students, you'll be knowing this. So in this compound microscope, you have two important lenses. One is called as the objective and the second is called as the eyepiece, right? So here, if you see, this is an idea which is derived from the combination of, from the concept of combination of lens. So if you revisit the concept of combination of lenses, you can observe that the effective magnification when two lenses are in contact is given as M1 into M2. It is going to be M1 into M2. So this is the logic that is used to design this kind of a material. So what I'm going to do is, I gave you the outline, but for you to understand this concept, I want you to master the concept of simple microscope. So I suggest everybody to practice it today, so that in tomorrow's class I can complete compound microscope and telescope at a stretch. Okay, so that is a very simple concept, but as I mentioned, you need to revise the concept of simple microscope on your own so that you're able to do problems without seeing. Only then you will understand this diagram. Look how complicated it is. Right? Only then you will be able to understand this diagram. And secondly, you also revisit the concept of combination of lenses as well. Is that clear, guys?
Yes, sir.
Right. So this notes, I'm sharing it in the group. Just wait for a minute. So I'm sharing it in the group. Okay, I've done it. So take these notes, revise and study about these uses. And in tomorrow's class, ensure that you have no doubts with respect to simple microscope for you to understand what is compound microscope. Okay, this is very simple, nothing to worry. So in tomorrow's class, I'll be completing this chapter. Right? Any other doubt from today's class?
No, sir.
Guys, any doubt? That's good. Okay. So that's it from my side for today. You guys can log off.
Thank you, sir.
Thank you, sir.
Thank you, sir.